So welcome back to Advanced Higher Chemistry Unit 3. This is our final video on volumetric analysis. And we're going to be looking specifically at probably the most difficult type of titration known as a back titration. Now this type of volumetric analysis requires two titrations, sometimes just a reaction and then a titration to happen. Now your first experiment is either going to be a titration or a reaction, is where you take a chemical with an unknown quantity and you react it deliberately with a known excess of a second chemical. So that chemical you react it with is in excess. What that means is that not all of that excess chemical is going to react. There's going to be some left over. And obviously the amount left over is going to be dependent upon how much of chemical B, the first chemical, there was. Then what you do is you take your unreacted chemical A and titrate it against a standard solution. So you can work out exactly how many moles of chemical A were left unreacted. You know how many moles of chemical A you put in at the start. So you can then work out the difference. That tells you how many moles of chemical A reacted, from which you can then work out how much of chemical B there is. So based on how much of chemical C is needed, you know how much of A reacted and can work backwards to find out how much of B there is. So this is it sort of drawn out in a slightly different format, a bit more algebra representation. So our first reaction, we have A, which is in excess, reacting with B. And so we're producing a product and we're also left with excess A left over. We then take that excess A, do a titration with chemical D. Now the concentrations of A and D are known. So at the start of each reaction, we know exactly how much of A we put into experiment 1, and based on a titration, we will know exactly how much of chemical D we use in the second one. We can use the moles of our chemical D to determine how much of A was in excess, what was left over. Based on how much of A was left over and how much of A we know we put in, we can work out how much of A reacted. And based on how much of A that reacted, we can work out how much of our unknown chemical B we must have had. So you have to work backwards to end up with your result, which is why it's called a back titration. Now, where are back titrations used? Well, mostly they're used for chemicals that aren't very soluble or chemicals that are completely insoluble. So the first step is, rather than a titration, it's reacting your solid with an excess of a chemical. Then you do your titration and work backwards. That's the most common situation. And we can use back titrations to determine how much of an active ingredient there is in a pharmaceutical. So for example, if you make aspirin or if you're testing an unknown sample of aspirin, you can work out exactly how much of the active ingredient there is. Similarly, if you've got an alloy that you know is made out of two metals, if you add in an excess of a chemical that will only react with one of the metals, you can then use a back titration to find out how much of that particular metal is in the alloy. Now, in back titrations and in many volumetric analyses, we need to use a control. And in chemistry, particularly in analysis, a control is not the same thing that you would say in biology. A control is not to prove that your results are coming from the thing that you've changed, which is what it is in biology. A control in chemistry, in analysis, is something that you do to prove that your methodology actually works. So what you do is you test your method on a chemical that you know the exact concentration or composition of. And then you apply your methods, and you should be able to work backwards to prove and show that it contains exactly what you know it contains. If you don't get a match to what you know it should be, it means that there's something wrong with your methodology, and you can then look at what you need to change. So this is used particularly when testing for things like aspirin. If you're wanting to check that your method tests successfully for aspirin, you would use a purchased sample of aspirin that has an exact dose. Prove that your methodology shows that exact dose, and then you can then use your methodology on unknown samples. So control means something slightly different than in biology, but it's a way to prove that your methodology works. Now, what I'm going to take you through is an example of a back titration, one that you hopefully will get to try experimentally, which is checking the purity of marble. Now, marble is a form of calcium carbonate. If marble is pure, then it should be 100% calcium carbonate. However, most marble chips, marble powders, will contain some impurities. Calcium carbonate is insoluble, so normal titrations are not possible, which is why you have to use a back titration. The methodology we're going to use is weigh approximately, that says 1 gram, 2 grams of marble, and we'll react it with an excess of standard hydrochloric acid. Then take a sample of the remaining solution and titrate it against standardized sodium hydroxide. Now remember, the reason why I'm saying standardized sodium hydroxide is that sodium hydroxide is not primary standard, and so it will need to have been tested against a primary standard for us to know its exact concentration. Then after we've done the titration, we'll be able to work backwards, see how much sodium hydroxide was needed, therefore how much hydrochloric acid was left in excess, how much hydrochloric acid therefore reacted, and based on that, what mass of calcium carbonate reacted, and therefore what the purity of the marble was. Now the equations we're going to use, calcium carbonate reacting with hydrochloric acid occurs in a 1:2 ratio, and then sodium hydroxide reacting with hydrochloric acid reacts in a 1:1 ratio. It is always important to keep both equations in mind so that you keep yourself straight whenever you're doing your calculations. Make sure you know for each equation which one is being used, what is the molar ratio. So doing our reaction. So we're saying we've weighed out 1.98 grams and we've put it into a 250 centimeter cube volumetric flask. So we're actually doing the reaction in a volumetric flask. We then add, using a pipette, 50 milliliters or centimeters cubed of 2 molar hydrochloric acid. Now this is an acid reacting with a carbonate, so it's going to fizz as carbon dioxide is produced. Now it's best to leave the flask unstoppered for several hours or overnight. Now the reason you need to leave it is so that all of the marble chip has time to react. It should react quickly, but some chemicals are slow. The reason you need to leave it unstoppered is because carbon dioxide is being produced, and if you have a stopper on it, you'll build up pressure inside the flask. So it's to make sure the marble fully reacts and to make sure that all the carbon dioxide can leave. Then, once it's done, you're going to top up your solution so that you have 50 milliliters. You're going to top it up to the 250 mark, so you're diluting this down to make a 250 centimeter cubed solution of hydrochloric acid. Then we need to do a titration. Now again, remember, sodium hydroxide is not a primary standard, so it needs to have been standardized against oxalic acid. we're going to use 20 centimeters cubed of our hydrochloric acid in a conical flask, and we're going to do a titration with our sodium hydroxide solution, which we standardized and know is 0.1 mole per litre. We do the titration, we end up with an average titer of 49.2. We can then do our calculations. So the first calculation, remember we're working backwards, is going to be based on our second equation, our sodium hydroxide reaction with hydrochloric acid, which is a 1-to-1 ratio. Now the moles of sodium hydroxide, N equals CV, so it's 0.1 mole per litre multiplied by 0.0492 litres, which gets us that 0.00492. Because it's a 1-to-1 ratio, we know that that is the number of moles of hydrochloric acid in 20 centimeters cubed. Make sure that you note that down, that was in 20 centimeters cubed. Because our second step is we have to work out exactly how much hydrochloric acid was left unreacted. And we only took a sample of all the hydrochloric acid, so we need to scale it up. Now in 20 centimeters cubed, we had our 0.00492 moles of hydrochloric acid, but we know that we made a total of 250 centimeters cubed. So we need to use proportion. It's going to be 0.00492, divide by the 20 to tell us what 1 centimeter cubed is, then multiply by 250 to tell us how many there were in our big flask, which works out at 0.0615 moles. Now, we don't need to change that at all because the number of moles in our 250 centimeters cubed is exactly the number of moles that we had at the end of reaction. Okay, because all we did was dilute it, so we changed the concentration, but the number of moles stays the same. So 0.0615 was our excess unreacted hydrochloric acid. Next step is work out how many moles of hydrochloric acid did react. So to do that, we need to use that value, the unreacted value, and also work out how much hydrochloric acid we actually used at the start. So it's going to be N equals C times V. We used 2 mole per litre acid and we used 50 centimeters cubed. So that gives us 0.1 moles was used. But there was 0.0615 unreacted, so if we subtract it, we know that the moles of hydrochloric acid that reacted must be 0.0385. Finally, we can calculate the moles and the mass of calcium carbonate. So the moles of hydrochloric acid that reacted, we have just proven was 0.0385. From the mole ratio, the number of moles of calcium carbonate is going to be, because it's 2 to 1, we're going to have to divide that by 2, which gives us 0.01925 moles, which we can turn into a mass by multiplying by the gram formula mass, which is 100.1, which gives us 1.93. Now, because that's our final answer, we're going to write it to 2 decimal places. All of your working out in the middle, keep the numbers really complicated, only at the end, round up to your 2 decimal places. Now we could finish there. That's the mass of calcium carbonate in marble, but we were wanting to find out what the purity was. So to do that, we work out purity as a percentage. The mass of marble we used was 1.98 grams. The mass of calcium carbonate we've proven reacted from that marble was 1.93 grams. So to work out percentage purity, it's our calcium carbonate divided by our mass of marble as a percentage. So 1.93 divided by 1.98 multiplied by 100, which gives us 97.4%. Typically, for something like marble, we would expect the purity to be 90% or higher, and so 97.4% would be an acceptable answer. I know that that worked example is quite long, and it does take time to do a back titration. It is possible that you could get a back titration as a paper 2 question. However, it would be likely that it would be broken down into steps, because those 5 steps altogether would be worth more than the maximum number of marks that is ever given for a question, which is 3. Okay, so I don't want you to be too worried. Just with some practice, you can get these to work. Okay, so that has been all of volumetric analysis. You'll be pleased to hear that all future topics in this unit will be one video to cover everything for each topic. Okay, I'll see you in the next one.